Thank you for coming back. You made it to day 6. We're halfway through after today. Pretty crazy. But the fun hasn't even began yet. So welcome to day 6 of the Data Science Decal, October 10th. We're grading our first project right now. It's going, and hopefully we'll get your scores back soon. Don't worry if the score is less than what you hoped it would be. We anticipate that with enough effort you will all pass. If you are worried about your standing in the class, please come talk to us. I'm a bit of a harsh grader. My peers are a little bit nicer, but I'd like to give you an accurate representation of where you are in the class. So SVMs. Does anyone know what an SVM is? What is an SVM? Yeah.
Support vector machine.
Yeah, support vector machine. Really, really popular and useful algorithm that's really, maybe not in the last couple of years, but preceding that has been very popular for most classification techniques. So here we have Nikita. Nikita will be talking to you about SVMs, support vector machines, as well as she'll also talk to you about a general framework for how to have a good understanding of machine learning and what to do when your models are doing certain things. We will be releasing your second project. Actually, the second project is released, and more on that will be touched upon later by Nikita. But for now, stay tuned. Let's get started with SVMs. Here's Nikita.
Okay. Hello? Okay, so like Jordan mentioned, today we'll be talking about SVMs, and afterwards I'll cover like some good machine learning practices. So first, for an overview on like what SVMs are. SVMs are a supervised classification algorithm like logistic regression. But what's special about them is that they find the optimal decision boundary between the training points, and I'll define later what optimal actually means. And like Jordan mentioned, SVMs were very widely used in practice, and like I'll cover some of the pros and cons of them also. So before we can talk about like really what they are, there's like some vocabulary we need to make sure we're all on the same page about. So if anytime during this lecture I'm like using a word that you don't understand, like please ask about it, because only then like you'll actually understand the rest of it. So like the main thing about the SVM is that it finds the optimal decision boundary or the optimal hyperplane. And this basically means that it correctly separates all the data points if possible, but it finds the decision boundary that's furthest away from all the data points. So you can see here that there's like a bunch of green decision boundaries that accurately classify this training set. But the red one is the one that's furthest away from all the data points, so it's like right in the middle of the area where the decision boundary should be. Yeah. So the way that we find that what the optimal hyperplane is by calculating the margin. And the margin is the empty region that has no data points in it, and that's usually where the decision boundary will be. So you can see here that I drew like gray lines near on the two training points that are closest to the decision boundary, and then the red line, which is the decision boundary, is right in the middle of it. So you can think of the margin as twice the distance from the hyperplane to the closest data point. Any questions on any of those two vocabulary terms? Okay. So support vectors are the points that lie on the margin or violate the margin. So in this case, we have linearly separable data. So the support vectors are this point and that point, the highlighted ones. And they're the support vectors because they lie on the margin, and they're the closest to the decision boundary. In the non-linearly separable case, this you can see is like probably better suited if we use some sort of a quadratic function to fit it. But here we use the linear function still. So the support vectors are the ones that not only lie on the margin or inside the margin, but also they violate the margin and they're placed on the wrong side of the decision boundary. So that's why we have this orange point here and this blue one over there. The reason why support vectors are important is because they're the ones that directly influence what the decision boundary is. So for example, in this case, let's say we took this blue dot and moved it a bit closer to the red line. Right now, the red line has to basically be in the middle, so it'll be moved further down also. So the support vectors are the ones that directly influence what the decision boundary is. So why are we using SVMs in the first place? SVMs pick the optimal hyperplane, which allows the model to generalize well. So for example here, or actually in this example, you can see that, let's say we pick this green line to be our decision boundary, right? Right now it's classifying all the training points accurately, but let's say that we had another blue point that was a bit more noisy than the rest, so it was like a little bit further down, like over here. Right, that blue point would be classified incorrectly if we chose this furthest most green line to be the decision boundary. Right, so if we pick the decision boundary to be kind of in the middle, exactly in the middle, furthest away from all of them as possible, that allows for the best generalization because it basically gives both classes the most room for error. Again, like I mentioned before, SVMs are not really sensitive to outliers because they're basically determined by the support vectors, not by the outliers in the data set. So for example, let's say we had an orange point like way out over here, right? If we use something like least squares, where we're kind of averaging out all the data points, the line would overall be more flat because it'll be influenced by that outlier point. But with SVMs, as long as it's on the right side of the decision boundary, it actually doesn't really matter because it's only the support vectors that determine what the decision boundary is. Also with SVMs, kernel functions can be easily integrated, and that allows for an efficient computation of nonlinear features. And I'll get a lot more into that later, but essentially the idea of that is here you have a quadratic data set, and you would need some sort of quadratic function to fit it. And you can efficiently do this using kernel functions in SVMs. Okay, so does anyone have any questions basically? Yeah. Yeah, the support vectors are the points that, basically they're the points that are closest to the decision boundary. Yeah.
What's kernel function?
So I'll go over kernel functions like a lot more later, but they essentially they essentially allow you to lift your data points into a higher dimensional space so you can still fit it linearly even though it's something like quadratic. So there's two types of SVMs mainly, hard margin and soft margin. I'll be going into the differences between both of them and also how to formulate their optimization problems. One thing to note, for like the next few slides, it'll kind of assume a pretty basic understanding of multivariable calculus and linear algebra. If you are confused with any of those concepts, try to understand and focus more why we're doing a certain operation rather than how the operation is done. And later I can explain it in more depth if you want. Okay, so in the hard margin SVM case, you're trying to maximize the margin while requiring that all of the data points are classified correctly. So that means you're not allowed to have any support vectors that actually violate the margin and go to the other side. So if the training set is linearly separable but it's noisy, it might be a little hard to actually classify it perfectly, right? So in that case, a nonlinear kernel might have to be used. So basically fitting a higher dimensional decision boundary like quadratic or cubic when the training data is actually probably linear when you look at it from a bigger picture. So the issue with this is that it'll cause high variance or overfitting because if you have a decision boundary that perfectly fits your training set, that really doesn't allow for good generalization when you have a test set it's basically the same, but it's slightly different because the noise might be a little different, right? So I'll go into more when to use hard margin SVMs later, but the main takeaway is that all the training points have to be classified correctly for this one. In a soft margin SVM, you don't necessarily need to classify every training point correctly. And the way that we do that is each data point xi has a slack variable epsilon I associated with it. And we're basically picking and choosing certain points that we think are allowed to violate the margin and be misclassified and giving them a slack variable epsilon I that's greater than 0. And I'll talk more about what that exactly means later on, but you incorporate the slack variable into the loss term, and that allows certain points in the data set to be misclassified for the overall data set to be more generalized. Okay, so which one to use? Hard hard margin SVMs, like I mentioned before, can overfit to training data, especially if the training data is non-linearly separable or very noisy or something like that. Whereas soft margin SVMs have a lot more versatility, and because we have slack variables, we can choose how much we're allowing the decision boundary to misclassify the training points, and that allows us to control the bias and variance. Have you guys gone over bias and variance so far? Yeah, okay. Yeah. Okay, so now like formulating the problem of a hard margin SVM. So again, we have this picture of our training points, and the red line is the optimal decision boundary, right? We have our weight vector W and the feature vector X. So in this case, X would be comprised of X1 and X2. The decision boundary will define it as the place where W times X, the dot product between both of them, is equal to 0. And then we'll define the two lines that are that contain the data points or the support vectors to be W dot product with X is equal to 1 and -1 respectively. So those are the edges of the margin. Yeah. So in a hard margin SVM, we want all the training points to be classified correctly, right? So that means let's define all the blue dots to have a class label of y equals 1, and all the orange dots to have a class label of y equals -1, right? If we want all the training points to be classified correctly, that means for all yi where it's 1, so for all these blue dots, we want the dot product of w and x to be greater than 1, right? Greater than or equal to 1, right? So if it's equal to 1, it'll be over here on the line, and if it's greater than 1, it'll be like any of these points out there. So we're basically enforcing that constraint. Similarly, if we have the class label as -1, we want the dot product of w and x to be less than or equal to -1. So it'll be all the points in this region or on that gray line. Does that make sense? Okay. So now just rewriting this a little bit. So we have these two constraints from before. And what we're basically going to do to kind of make this a little bit more compact is multiply both sides of the equation by yi. So if yi is equal to -1, we'll multiply both sides by that, and we flip the sign over here because you're multiplying by a negative number. And then you have -1 times -1 is equal to 1. And similarly, if we have yi is equal to 1, we multiply both sides of the constraint by yi, and that doesn't really change anything. So you again get that the dot product of wx times yi is greater than or equal to 1. Yeah. So the b variable is the bias term. So if you just had the dot product of w and x, it would go through the origin. So the b allows you, it's like in the equation of the line, it allows you to have like a certain y-intercept. But like depending on how you formulate your features x, you can actually incorporate a column of 1s into it so that when you compute the dot product of w and x, you actually don't have to include an extra b term added on. It'll just be included in the matrix multiplication. Okay. So we have this constraint. So, actually here. So in both of these cases, what you can see is that after multiplying both sides by -1, we get the constraint that yi times the dot product of w and xi is greater than or equal to 1 for both the case where it's yi is equal to 1 or -1. Does that make sense? Okay. And then again, from before, the margin is bounded by the hyperplanes where the dot product of wx is equal to 1 and -1 respectively. Okay. So now, yeah.
Wait, what exactly is a hyperplane? Is it just that line?
Yeah, it's the decision boundary. So in 2 dimensions, it's a line, but in 3 dimensions, it can be a plane. Okay. So in SVMs, we said that we wanted to find the optimal hyperplane, and that happened from maximizing the margin. So in order to maximize the margin, we need to compute what the width of the margin is, right? So again, in this picture, we have these two as the support vectors, and we'll call this blue point x plus, and this orange point is x minus. And if we take x plus minus x minus, you get this vector over here, right? So this vector connects the two gray lines together, basically. But that's not how you find the distance, because that's not necessarily the shortest distance between the two lines, right? You want to find basically the perpendicular vector that goes through it. So the weight vector is always perpendicular to the decision boundary. So that's why W is perpendicular over here. And to find the width of the margin, we can project x plus this green line basically onto the weight vector. So we have the direction from the weight vector, and we have the length of it kind of from this one. And once we project them together, we'll figure out what the width of the margin is. Does that make sense? Okay. So for support vectors, so basically now we'll just actually plug in what the support vector formula is. So for support vectors, we know that the dot product of wx times y minus 1 is equal to 0, and I just subtracted the 1 on both sides. So when yi is equal to 1, if you plug in yi is equal to 1 here, that means the dot product of w times xi is equal to 1 minus b. And similarly, when it's negative 1, the dot product is equal to negative 1 minus b. And we know that this one is, we defined it as x plus, and this is x minus from the previous picture. So when you plug in both of these equations into here, we'll get that the width of the margin is equal to 2 over the norm of the weights vector.
What is y again?
Y is the class of the training point, so it's either 1 or negative 1. Okay. So essentially, we're trying to maximize the margin, right? And we know that the margin is equal to this formula over here, 2 over the norm of w. So to maximize the margin, we're minimizing the norm of w. So now the problem is we're trying to minimize 1/2 the norm of w squared. And the reason I did this is because it makes it easier for, in order to kind of find the minimum of this if you have a quadratic term. And we have the constraint that y times the dot product of w and x minus 1 has to be equal to 0 for all the support vectors. So like how we did, or actually, yeah. So then taking this, we can create a loss function over here. So the loss function, we're minimizing this term, so it directly comes over here. And then I subtracted basically the sum over all the alpha i's times this term over here. And basically what that's meaning is when alpha, and we let alpha I equal 0 for non-support vectors. So for any points that are not support vectors, don't include them at all in the loss term. But for points that are support vectors, we want them to be correctly classified. And the reason, or like basically if yi is equal to 1, but we predict it to be negative 1 over here, because this is the predicted value and this is the true value, right? That means that this overall term will be a negative number, and we're subtracting 1, so that means this overall term is a negative number. And when you subtract a negative number, you're adding a positive number, right? So that means the loss essentially went up whenever you misclassified a support vector. Similarly, if you correctly classified it, yi and this term will be the same. So whether it's 1 or negative 1, this term will always be, the overall term will always be a positive number. So you're subtracting a positive number from the loss. So you're basically decreasing the loss when you correctly classified a support vector. Does it make sense how I went from this statement to that loss term? Okay. So now that we have the loss term, we're trying to find the minimum of this. So you can just take the derivative. And first we'll take the derivative with respect to w because you're trying to find the optimal w. And when you do that, you get that w is equal to the sum of alpha I, yi, xi. And similarly, when you take the derivative with respect to b, you get that the sum of alpha I, yi is equal to 0. Yeah. Wait, sorry, can you speak up?
Provide the yi times the plus b, and when it's always 0, it has to be 0. The sum of those things has to be 0.
You're saying,
The ai times 0
right, so it's not actually that each alpha I times y is equal to 0, it's the sum of all of them. So that means once you multiply on xi, it's not necessarily that the sum is 0.
Why do you take it with respect to b?
Because you're trying to find the optimal w and b, but like when I'm going forward, I'll just focus on with respect to w. So this part isn't too important to know exactly how to take the derivative and stuff, but the conclusion that you get from this is kind of useful to understand why kernel functions are important. So that's why I'm like covering it at a very high level. Okay, so we know that there's some sort of critical point at w is equal to the sum of alpha I, yi, xi. So you can take that and plug it back into the loss function that you had before. And essentially, once you simplify all this out, it's not too important to know how to do that, but once you simplify it out, you can see that the loss term depends directly on xi times xj, right? So that means pairs of different training variables. Right, so the optimization problem depends on the dot product of the pairs of samples. And that's just something, remember that when we get to kernel functions, that'll be pretty important. Okay, so now we'll just do the same thing again at a higher level for the soft margin SVM problem. Like I mentioned before, for soft margin SVMs, you don't necessarily have to classify each point correctly. So some points, if their slack variable is greater than 0, can violate the margin and be misclassified. So the constraints are changed now that the dot product of yi times wx is greater than or equal to 1 minus epsilon I. So support vectors that violate the margin have a positive epsilon I. So that means if we remember in the previous diagram, you have a line where the dot product is equal to 1 and negative 1, right? And if it's less than that, that means it'll be inside the margin. So we're basically allowing certain samples to be inside the margin. And then support vectors that are on the margin have the dot products is equal to 1. Okay. So kind of following the same steps as before, I skipped a lot of steps in the middle. The optimization problem ends up being that you're minimizing the norm of w squared plus some constant c times the sum of all the slack variables. And in this case, we're summing up all the slack variables and adding it to your the term that you're trying to minimize, because if you have, we're allowing the slack variable to be positive if it's violating the margin and being misclassified. So if you allow basically every point to be misclassified, that means the sum of all the slack variables will be really large, and this would allow your data set to generalize, your model to generalize, but it would also cause it to be having a very low accuracy, because you're basically giving it the freedom to misclassify every point, right? So we're allowing it to misclassify some points, but we're trying to keep that at a minimum, so that's why this term is added on to the minimization term. And similarly, we have the same constraint as before. This term C is a regularization hyperparameter, so it basically controls how much are we allowing the model to misclassify points. And similar to the hard margin SVM problem, after solving the soft margin problem, we find that the optimization problem only depends on the dot product between pairs of samples. Okay. Any questions on any of that, like how we came up with the problems for both of them?
Which pairs are you considering?
So basically, for each xi point, it'll consider every other xj point. Yeah.
Did you notice the inequality again? What is that inequality sourcing?
Yeah. Okay. So in this photo, we have that when the dot product of wx is greater than or equal to 1, that's like all the region over here, right? And in the hard margin SVM problem, we're forcing that that's true. But let's say that we're allowing our soft margin SVM to misclassify this point, right? That means the margin would actually be placed at the next closest point, which is like probably that one, right? So in that case, this would be wx equals 1, and this would be wx is equal to some term greater than 0 but less than 1. So we're basically giving that freedom by putting it into the constraint. Yeah?
When we use SVMs to find boundaries for decision trees, or is that the use of them?
I don't think it can be.
Yeah.
Oh, okay. Do you want to talk about that?
Yeah, you can use SVMs to find like decision, or like to find splits in decision trees. It's possible.
Okay. So I guess I'll go on to kernels then. kernels are, or actually before we had the example where we had a data set that looked like some sort of quadratic function would best be able to fit it, right? But when we fitted it with a linear function, that ended up misclassifying a lot of points. So in this example over here, let's say that this is the x-axis and these are all our training data points, right? No matter what type of linear classifier you use, like let's say you drew a line like this or like this, no matter what you did, you wouldn't be able to classify everything correctly, right? You need some sort of a higher dimensional classifier. So what we can actually do is take all these points, apply some function to them, and lift them to a higher space. So for example, let's say we applied like some quadratic function that was centered around like somewhere over here. Then this data set would turn out to be something like this. Yeah, and once we have something like this, now you can see that all the orange points are like clustered right at the bottom, so we can easily draw a linear separator between both of them. And actually, there's a video that kind of explains this nicely. Okay, so in this example, you can see that the blue and the red dots, so it's kind of hard to see, but these are all the red dots and the blue dots are in the middle. They're not linearly separable, and only when they use like a circular decision boundary, it was separable. So what you can do is take them and apply some sort of quadratic function to it. So now you can see that all the red points are lifted up above, and then the blue points are left down below. And once you apply this function to the data set, now you can fit the thing linearly with some sort of a hyperplane. And also, like I was mentioning, optimal hyperplane, it can be a plane like this also, not just a line. All right, so you can fit it with a linear hyperplane now. And if you look, even though the plane is linear in this higher dimensional space, if you look at its projection onto the data space, it's like a circle, right? So that means when we take this data set and transform it back down into its original space, the decision boundary is actually circular, not linear, even though it was linear in some higher dimensional space.
Why do we like want it to be linear?
Linear boundaries are usually easier to compute, and you can use the same techniques that you've learned before, so yeah. Okay, so in this example, let's let phi of x be the transformation into the higher dimensional space. Okay, so in both the hard margin and soft margin SVM problems, we said that the loss function was dependent on the pairs, the dot product between the pairs of the training points, right? So after applying this function phi of x onto it, the optimization problem would depend on the function applied to each of the xi, xj, right? And you can compute it like this, but let's let a function k of xi, xj equal to this. So it's after the transformation is applied to each individual xi, xj point. Kernels for SVMs allow us to basically compute this this dot product, which is needed for the optimization problem, without actually directly computing phi of xi. So it's a bit more of an efficient way to do this. And an example to kind of make this more clear. So let's say you have a data set that needs to be like, it needs like some sort of quadratic decision function, right? If you wanted to take your x vector and make that quadratic, you would have to take each individual feature in x and square that, and compute all the cross products between various features. So for example, you would have to have like x1 squared, x2 squared, x1, x2, and you would have to keep computing like that. And that ends up, especially when you have a large data set and you want to transform this to a very high dimensional polynomial, that ends up being very memory and computationally inefficient. But what we can do instead is that we know that for an SVM, the loss function only depends on the dot product between the pairs of samples, right? So we don't actually have to compute what x1 individually or each xi individually is transformed to the quadratic space. Instead, we can just compute what the dot product between 2 points are. So this is kind of bad notation, but when I have y over here, it doesn't mean the label y. It's like just another training point. So just think of this as xi, xj. We can actually compute this polynomial by saying 1 plus the dot product of xi x and y raised to the pth power. And concretely, if x is equal to x1, x2, and y is equal to y1, y2, and we're computing it to the second polynomial, so basically we want each variable in x to be raised to the second and each variable in y. That expands out to this term over here, which is what we want. But we never had to individually compute it for each x and y, because we could just compute this equation instead. And you can also represent this as a dot product between two vectors. Okay. So if we're computing a degree p polynomial and we have input with d dimensions in it, so d different features, that'll be on the order of O of d to the p time, which is really large, especially as you have a lot of features or a lot of dimensions. And this is if you do it without kernels. But if we do have kernels, we can compute this function but in O of d time, even if the dot product itself has a length of O of d to the p. So over here, even though this dot product, once you write out the summation, is really long, you can actually compute it because here we have x's in two dimensions, right? It has x1 and x2, and similarly y has two dimensions also. You only have to go through each of the dimensions once to compute the dot product. So we only had to expand out two terms over here and then just compute the expression instead of actually having to expand this all out, even though this is actually equivalent to that. So the overall idea of kernels is that whether or not you're actually computing a transformation on an individual xi, the equation k of xy will converge to what it would be. Yeah. Any questions on that? Okay. So initially when we had our decision function before, so we're trying to create the decision boundary, that was equal to the dot product of w, and if we're finding it with respect to z, it's the dot product of w and z, right, which can be written out in the summation form. If you have kernels, you can just modify this slightly by saying that it's the dot product of w times the vector that would arise if we computed the kernel function on each xi pair with the variable you're trying to predict. So it's just a slight modification to the original problem. Okay. So we talked about polynomial kernels. Another kernel that's really useful and popularly used is the Gaussian radial basis kernel. And this, how many of you guys have seen Gaussian distributions before? Okay, cool. So basically, the kernel function is equivalent to this, which is actually it looks pretty similar to the PDF of a Gaussian, right? And we can take the sigma term and put it into this constant gamma over here. So gamma is equal to 1 over 2 sigma squared. And it's always positive because sigma squared would be a positive number. And the actual vector phi of x would be an infinite vector because if you take, if you're trying to approximate a Gaussian function using Taylor polynomials, that essentially goes on infinitely. But the dot product between both of them converges to this expression over here. So that's that really showcases why kernels are really important because you're able to compute an infinitely long polynomial in a finite way with that expression. Okay. So with all this, it's not so important that you understand exactly how the kernel is functioning and stuff, but it's more important to understand how, when you change different parameters, the kernel and the model respectively will change. So over here, if we make gamma really large, that means 1 over 2 sigma squared is going to be very large. So that means sigma is very small. So the variance is very small. You can think of that as this blue curve over here, where it's the variance is really small, but the peak is very high. That makes the Gaussian narrow. And so then when you compute the dot product between 2 points, let's say one point x is at 0 over here, so its y value is right there at the top of the peak. And another point is at x equals 1, so its y value is over there. Right? When you compute the dot product between both of these, because they're very far away, the dot product would be a very small number. So that means k of xy would be a very small number. And essentially what all this means is that this essentially causes the model to be very dependent on points only very close to x. So the kernel function will only have a large value when you're computing it with respect to another point that's really close to the original point, right? So points far away have no influence or very little influence on the class of x. This overall allows the model to be much more expressive because each x point is almost treated very individually. So your error rate will go down very low for your training set, but also this might not generalize so well because what's very specific to one data set will not hold the same for the test set, right? Okay. So the Gaussian kernels can specifically be thought of as a similarity function where k of xy assigns high values for points that are near each other. So like over here again, let's say you had a point that was at the top of that would map to the point over here at the top, and another point very close to it, right? Like really close. That's like right over here. Then the dot product would be an overall high number because they're very similar to each other, right? So going back to the whole gamma and sigma thing, if we made the variance very large, that means that the Gaussian function would be very flat, right? So that means whether you choose x0 and x3, the difference in y's aren't too different. So the kernel function would still return a pretty large number. So that means points that are far away from the point that you're trying to predict still have a pretty significant influence. Does that make sense? So why are we using Gaussian kernels? Because they allow you to have a smoother decision function. If you think about like k-nearest neighbors, where the class of each point is determined by the class of the points around it, the Gaussian kernel has some sort of similarity metric like that, and you can control how much of a similarity metric you want by making gamma either really large or really small. So it combines basically the similarity metrics of k and n's, and also the kind of overall averaging of a data set that you see with traditional SVMs and other methods like logistic regression. So this oscillates less than polynomial kernels depending on what you choose the value of sigma to be, because if you make the variance very large, that means every point really affects the class of one particular point. And again, sample points that are closer to the point that you're trying to predict would have a greater impact on the prediction of the point that you're trying to predict. Okay, SVMs in practice. So overall, now that you kind of understand the intuition behind SVMs, the good parts about them is that they find the optimal decision boundary between data rather than just finding some decision boundary between the data. And they also can capture complex nonlinear relationships using kernels, and that's more efficient than manually computing the features. And another thing that's pretty cool about them is that even though you can have, like for example with the Gaussian kernel, right, you have a very high dimensional polynomial if you try to expand it out. But the way that SVMs are optimized, which I won't really go into here, but it allows you to optimize it and find the minimum while still trying to maintain the simplicity of the model if you can. So using as little features as possible. But the cons are that if you have high dimensional features and you have a really large input size, this is better than manually computing the features, but it still takes a long time. And also, after you transform the data using the kernel trick, it may be hard to interpret depending on which kernel you use. So oftentimes SVMs are treated as a black box. And actually, if you look at feed-forward neural networks, which you'll cover in the next lecture, SVMs for particular data sets can perform pretty well and are very comparable to feed-forward networks. But one advantage of them is that you can optimize it without getting stuck in local minimum. And all this will be covered more next time. And also, they don't overfit as much as feed-forward networks do sometimes. So overall, they're a very powerful tool that it's a good idea to understand how to use it. So actually implementing an SVM is pretty challenging in practice, and it's probably a better use of your time to know how to use it well rather than how to actually code it from scratch, especially given in Python with sklearn we have so many libraries that help you out with this, right? So when you're actually using an SVM in sklearn, you have access to control what the kernels are, and specifically you have access to two hyperparameters, C and gamma. And C is used for the soft margin SVM, and it represents how unacceptable is it to misclassify data points. So if C is very large, that means it's very unacceptable to misclassify points, right? So in that case, you're basically saying all the training points, or most of them, have to be classified correctly. So that's actually pretty similar to a hard margin SVM. And this often results in small margins because especially if the data set is a bit noisy or whatnot, the support vector would be the one that's closest to the decision boundary. And it's also very sensitive to outliers in the sense that if your outlier is actually a support vector. And also, because you're very strictly saying that for the training set we need to classify everything correctly, you could run into the risk of overfitting pretty easily. On the other hand, if you choose a very small C, you're basically giving the model much more freedom to misclassify points. Basically, that allows the decision boundary that you choose to be much more generalizable, but as a result, it probably won't have as much accuracy. Also, do you guys understand how this loss function translates into these conclusions? Basically, if you have a very large C, that means this term overweighs the norm of W squared, right? So it'll focus more on trying to get everything correctly. But if you have a small C, it'll focus more on trying to maximize the margin rather than get everything correctly. Okay. So the other hyperparameter is gamma, and this applies for like the polynomial kernel, the RBF kernel, and sigmoid kernels in sklearn. So a small gamma corresponds to a very large variance. So your Gaussian distribution is very flat and wide. So each support vector has a greater influence on points that are far away from it. So this kind of results to a sort of averaging that causes the overall model to be less complex and this is the old version of the slides, but that basically results in lower variance, not higher variance. I think the slides on GitHub are updated with this though. It leads to lower variance models that don't overfit as much, but they have a lower bias. Whereas if you have a large gamma, that leads to models that, that basically means that each sample point really determines its own class. So you have very expressive models that are going to have higher accuracies, but are probably going to overfit more. Okay, so now I'll do a quick demo on SVMs. So you can see kind of how these hyperparameters actually affect things. Can everyone see this? Yeah, okay. So first we have like a simple 2D data set. So the X features have 2 dimensions and the Y are either class labels 1 or 0. And if you plot it out, it looks kind of like this. So you can see that for the most part it's pretty linearly separable, except you have this one blue point over here that kind of messes with things. And we'll see how changing the hyperparameters kind of tells the SVM what to do with that outlier point. So just as a recap, to choose C, a large C makes it very similar to a hard margin SVM, where your goal is to minimize few training points, and a small C allows you to misclassify much more training points. So over here, we have C is equal to 1, so we're basically allowing it to misclassify points easily. And we get that after you fit the model, it gets a score of 98%, which means that it probably misclassified the outlier. Yeah?
What does C usually range? Like what number does it range to? What's one?
I think it's probably dependent on your data set, but like in this example, like we're probably going from like 1 to 100, kind of. Okay, so it misclassified the outlier, and if we make C much larger over here, that means that we're saying if we make C much larger, we're basically trying to make it classified correctly. So in this case, we can up above we see that this one is supposed to belong to this class up here, right? So when C is equal to 1, it misclassified it and it made it the blue class over here, because we basically gave it freedom to misclassify things. But when C is equal to 100, you can't, oh, actually you can't really see it at all, but the point is actually like right over there, and it's a very faint pink color. And if you look at the difference between the decision boundary here and over here, you can see that the decision boundary over here is much steeper, and then it flattened out once you got here in an attempt to classify that outlier correctly. So you can see like the decision boundary is probably something like around there, right? Because these points have a lower confidence. Okay. When we have C is a greater number, the decision boundary is much steeper in an attempt to classify the outlier. So now if we look at a nonlinear data set like this one, we're going to show how kernels basically can allow you to classify something like this, where you can't really say what polynomial will classify this, but you probably know that it's like something that's really high dimensional. So for now we're going to train it on a gamma value of 100, so we're basically making the variance very low. And you can see here that each point is basically only, each point determines its own class a lot. So it basically classified the entire data set pretty perfectly, giving a very distinct class between these points and those out there. Whereas if you made gamma a lower number, right, like let's make it 1, right? Now that means that the variance is much higher, so you have a much flatter Gaussian model, and so overall it's going to do a lot more averaging, right? So when you run this, you can see here that the score when you're running it dropped from like some 90% to 83%. And when you plot it, you can see that there's much less distinction between the points of the inner class and of the outer class, right? And that was as a result of decreasing gamma. Okay, so when you're using class SVMs and sklearn, those are the main two things that you want to focus on to see what's best for your data set and your model. But a cool thing that sklearn has is grid search, and that allows you to basically find the optimal hyperparameters without manually having to go through and say like gamma is equal to 110 and like keep going like that. You can just create a list like over here with all the values of C you want to try, all the values of gamma you want to try, and let it pick basically what's the optimal one. And here it shows that the optimal one is when C is equal to 10 and gamma is equal to 100. And when we train the model using those hyperparameters now, you can see that it did a pretty good job of classifying everything. And yeah, there's like a bunch of faint pink points out there that you can't really see that are the other class. But yeah. Any questions on like how to actually use SVMs in practice and stuff? Okay. Okay, so we're going to take a break for a little bit and do like attendance, and then I'll go over what the project is. The link is tinyurl.com/xx-svm-xx.
Let me go through the responses. I'm sorry. Okay, they're open.
Maybe let's take like 5-minute break and then.
Yeah.
Can you just mention like homework for you, even though like in 2 weeks we'll include this stuff like SVMs, like parameter
But we're
return?
not going to see it.
No, not in 2 weeks. Yep. In 2 weeks? That long?
I think maybe.
Is it next week? No, I think we're releasing it in 2 weeks and it's due on Halloween.
The most simplest algorithm you can ever imagine. You basically like how to set up no training. And every time you see what you check, it's it works so well for so many things. Yeah. It's cool. Yeah. You can't even hear it. Oh, yeah. We'll go back to the demo. Yeah. Future press TV.
Okay, we're going to restart. I guess I'll go over a bit more about cross-validation because especially that'll be pretty important for your project. I don't have any slides on this, so but basically you have a training set, a test set, and a validation set, right? The training set is what you're actually using to fit your model. The test set is what you use to essentially report your model. And when I say fit the model, that means kind of fit the weights of the model. So like if you have W, the dot product of W and X, it's like actually determining what is W. But as you can see with SVMs, we had like various hyperparameters such as C and gamma, right? And you want to determine what is the best C and gamma to use. What you could do is you could use the training set to determine what the best hyperparameters are using something like grid search. But another way you can do that is have a separate set called a validation set, which is used to determine what are the optimal values of the hyperparameters. So you already fit your model on the training set. So you have what the weights are, and then you determine what the hyperparameters are using the validation set. And this basically allows that when you test on the test set, you have a little bit of an idea of what the test set might look like because the validation set is essentially held out from your training set, right? So you're not actually fitting W on it. So in a way, it's kind of mirroring the test set, right? But you don't have to actually compromise the quality of or the integrity of the test set by actually fitting anything to it, including the hyperparameters. So it's usually good practice to train on one thing, validate on something else, and then report your accuracy on a test set overall. Yeah. So that'll be important for the project. Okay. So I'll just go over what the project is. It's going to be due 2 weeks from now. So you'll have like plenty of time to do it. And we'll also have a homework that's going to be released in 2 weeks, and that'll be probably due a week after, I guess. So this project, you'll be doing sentiment analysis, and you'll basically be exploring various linear and logistic regression techniques and decision trees that you covered in the last lecture. So basically with this project, we'll be giving you a bunch of training data, which are movie reviews, basically. So you can see here you have a folder of negative reviews and like a bunch of text files for that. And you have like a folder of positive reviews, right? So you'll be training on these movie reviews, and you'll be overall determining, given a new movie review, is it a positive one or a negative? And there's multiple ways to do this, and you can actually use some pretty advanced techniques to do this really accurately. But for now, the goal of this project is just to kind of introduce you to the idea of sentiment analysis. And we'll be using a pretty basic model for this, and it's known as the bag of words model. So basically, you're computing the counts of each word. So how many times did each word occur in each review, basically, and that's going to be your features. So as you can imagine, like in a review, like you have a lot of different words, right? So there would be a lot of different features that you have. And like we mentioned before, too many features could lead to overfitting easily. So the goal of this project would be to kind of figure out which of those features can we remove, allowing us to get a higher accuracy and also allowing us to generalize better to the validation set. Yeah, so when you're going through, we listen to some of the feedback you gave about the last project, and we have starter code for this one. So we took care of reading in the file, basically taking, for the most part, creating a data frame out of each review and basically having a data frame of all the counts of each word. And we gave some methods that would be helpful for doing the tasks. And overall, what you have to do first is implement a logistic regression model on this data set, and then go through and see how you can reduce the features. And there's a lot of explanation on this, and once you try it out, we can help you a bit more if you're having issues with reducing certain features. But after that, you'll be trying decision trees. So you'll try both a single tree and a random forest tree, and then kind of explain which one works better and why is that the case. And then you submit the PDF of your notebook and also do like a write-up with like all the questions asked in here. So it's a pretty short project. It'll be due in 2 weeks. If you have any questions, let us know. And it's already released on GitHub. Okay. So I'll go back to the last part of the lecture then. And that is debugging ML algorithms and basically good practices in machine learning. The main thing that we're going to talk about first is like the bias-variance tradeoff, which you already covered, but like just as a review. So if you have a classifier that has a test error that's too high, but the training error is pretty low, so it's accurately classifying the training set but not the test set, you should check basically is the classifier overfitting or underfitting. And then just as a review from last time, if you have a model with high bias, that means the model is essentially too simple for the data set. So here we have something that should be quadratic, but we fit a line through it. So the error will be high, and the reason the error is high is because this model, no matter how well you try to optimize it, it's just too simple for this data set. Here's an example of balance. So it misclassifies a little bit, but overall it got the shape of the data set pretty well. And then a high variance model basically tries to classify everything correctly. So if this is the training set, you can see that it got every single point, but if you look at this, most probably if in the test set there could be a blue point that appeared over here, right? And it would misclassify that because it's creating a model that's too complex or too expressive for this data set. So those are like the differences between bias and variance. Yeah. So characteristics of high variance, if you're looking at how you're increasing more and more samples in your training set and looking at how the error is. Let's say you have a desired performance around here and the training set error roughly approaches it as you get more and more examples in your training set. But the test set error is much higher, and specifically what you can notice is that as you get more and more samples in the training set, the test set error decreases. So a high variance model means it's something that has the power to express too much, basically, right? And if you give it more and more points, it'll basically memorize those points a lot more, but it won't generalize well to another new point that you give. So that's why over here, as the training set size increases, there's not really much of a plateau here. It'll keep decreasing. Basically, it's trying to get every single training point possible for the error to go as low as possible. By contrast, a high bias model, which underfits, so it's a model that's too simple for the data set, the training error and the test error might be pretty similar, but the key difference is that the test error plateaus as the training set increases. So over here, you can add as many data points as you want and basically cover up every single point in that grid. But if you have a linear model, there's no way you're going to fit everything correctly, right? So after a certain point, it's like saying this is all the model can fit and the data set is just too complex for it. So that's why the test error actually ends up plateauing. So if you're plotting training set size versus error, these are like kind of the general shapes that allow you to diagnose whether you have a model with high bias or high variance. Okay, so if you have a model with high bias or if you have a model with high variance, you could do a variety of these things and basically take a minute to think about which of these things would fix a model with high variance and which one would fix a model with high bias. And you can talk to each other. Okay, so let's go over the solutions. Okay, if you have a model and you obtain more training examples for it, will it fix a high bias problem or a high variance problem? Can someone raise their hand? Anyone? Okay. So it'll fix a high variance problem, and essentially the reason is when we look at this plot, right, as you increase more and more training samples, if you have a model that's too expressive and you're not going to do anything to fix that, if you give it more examples, it'll probably fit better to the next example, because the goal is basically if you have a lot of training samples, you probably saw a bit of everything. So that's why obtaining more samples, training samples fixes high variance. What about if you reduce the number of features? Would that fix a high variance problem or a high bias problem? High variance? Yeah. And the reason is because, or actually, do you want to explain why?
If you have more features, then the model is more likely to fit to some sort of particular noises or idiosyncrasies within the model.
Mm-hmm.
So you're going to have more variance that's not very generalized.
Yeah, basically that's exactly correct. So if you have a model with too many features, that's a very expressive model, so it'll likely fit to the noise in the training set. What if you increase the number of features? Would that fix a high bias or variance problem? It's basically the opposite of the last one. Yeah, high bias. And do you want to explain why?
Yeah, so if you increase the number of features, then you can, I guess, fit to more aspects of the data. You can get a more complex model,
Mm-hmm.
and therefore you can, I guess, like overfit. It's not necessarily the right word, but you can overfit more.
Yeah. Yeah, that's correct. Basically, if you have something that has high bias, that means the model is not expressive enough. So if you give it more features, you're basically giving it more things it can manipulate so it can better understand what the distribution of the data set is. What if you're using do you guys go over regularization? Yeah, right? What if you use regularization for linear or logistic regression? What'll that fix? Yeah. Because if you use you're basically trying to minimize the size of the weights then, and it's allowing the model to become more simple. So basically you can think of it as if you have a high variance problem, make your model more simple. If you have a high bias problem, make your model more complicated. That's like the very general way to think about this. Any questions overall? Like this will be really important for your project. Like basically this is the main thing that you're going to be trying to fix. Okay. I have a bit about optimization objectives, but I don't think that would be as relevant, given that for the most part you're not actually implementing any of these algorithms, you're just calling functions from sklearn. So I'll skip this for now, but if you want to know more about this, you can look at the slides or ask me afterwards. So the last part is applying ML algorithms, and how do you basically create a complex ML model that has multiple components. So there's a few ways that are like kind of recommended. You could either design the various components of the algorithm beforehand, and then this allows basically for a more scalable algorithm because you know exactly what you want to do ahead of time. So it's like kind of equivalent to like doing a detailed pseudocode. But the issue is that it's hard to design it's hard to predict what the design of each component should be and without knowing how the other one's affected. And you also probably wouldn't know what to spend the most time on, and because you wouldn't know what's the hardest or most important. Another way you can do this is to just like come up with a quick implementation, do what you think is probably appropriate, and then go through and debug things like variance and bias as you go on. This usually allows it to work more quickly because you're only spending time on things that are broken. So we'll do an example. So let's say you want to do face recognition, right? You have a camera image as your input. You go through and pre-process all the data, and then you go into the face detection model. So first you want to segment from the pre-processed data. You'll segment out the eyes, nose, and mouth. And then you have 3 features from that, let's say. And you do logistic regression on those to get a label of what face it is. This is a very like oversimplified way to explain this, but it's just for an example. So if you have this model and you want to know how should I go about creating this, right? Or let's say you already built it really hastily and you want to know how should I best debug this, right? One way that you could do is error analysis. And basically, let's say that your overall system from beginning to end has an 85% accuracy, right? A good way to figure out which exact part of your model is broken, because you have so many different components which are feeding into each other, right? You should go through and plug in the true values for each component. So for example, you can go through and after pre-processing the data, what should the actual pre-processed data look like, and plug that in and see what the overall accuracy is. And let's say it becomes 85.1%, right? And then let's say you go through and say what should the correct values of all the i's look like, and then plug that in. And then if your model might go up to 96%, and then so on. And then essentially here, once you plug in the final values of logistic regression, because that's the last step, your model would obviously have 100% accuracy. So you can go through and look at the differences between each of these. So plugging in logistic regression gave it a 3% more accuracy, whereas over here, plugging in the I segmentation gave it almost 10% more accuracy, right? So you know that the I segmentation portion of your model has the most room for improvement. So you can go through and kind of debug from there, like what's actually going wrong there, and how do you fix it, right? Like maybe you would have to create a new model there or use like a different algorithm or something. But yeah, that's basically, if you have like a more complicated model that has multiple parts, like that's one way to go about debugging it and building it. And yeah, that's like about all I have. Are there any questions on anything I covered, like SVMs or this or the project or anything?
How do you know I is the most room for improvement?
So if you went through and when you're training the I segmentation part, right, you have your the true values that it should be, right? That's what you're training your model on. If you just inputted the true values as the output of the I segmentation, so instead of actually running your model, just give it the correct answers and then run the rest of the model on it, you can see that the accuracy of the overall model went up so much, right? So yeah, does that answer your question?
So it went up from 85.1.
Yeah, so basically, before you plugged in the true values, it was 85.1%, and then after you plugged in the true values, it became 95%, and this is the accuracy of the overall model, not just the I segmentation part. Right, so you know that this is where like most of the issue is coming. Any questions on like validation and any of that stuff, hyperparameters? That's also a pretty big part of your project. No? Okay. Yeah, so that's all I have for today.
Thanks, Nikita. Cool. SVMs are really, really good at what they do, actually. And seriously. So, Project 2 was released. It's due in 2 weeks. You will need to work in groups of 3 to 4 like last time. It should be quite a bit easier than the first project, I hope. I will say that project quality and like your analysis and like how far you go into it is a big part of the grade. I don't really care about your code for the projects. I care about you understanding what you're doing and interpreting your results and taking away insight, not just using sklearn and calling it a day. So project 2, so we switched the project 2 and homework 3. I apologize for that. So project 2 will be due in 2 weeks. Homework 3 will be due a week after that, and then we'll be back on schedule. Homework 3 will be support vector machines and hyperparameter tuning. Project 2 should be fun, I think. It'll be sentiment analysis, so it'll actually give you guys experience working on like a really, really applicable problem in a lot of domains. So it looks like we finished a bit early today. It's about 6:30. The staff will stick around if you guys have any questions or concerns. If not, thanks a lot for coming, and we'll see you next week for Neural Networks Day, baby. Let's get it.